In this lecture, we discuss about the method of tracing of Cartesian curves. Means if we have given a Cartesian curves, then how to trace that Cartesian curves. Suppose the equation of the curve is given by y is equal to f of x. Then we can trace for tracing the curve, we check the following points. The first point is symmetry. There are following symmetries. The first one is the about x-axis. If all the powers of y are even in the given equation of curve, then the curve is symmetric about x-axis. Let us take example y square is equal to 4ax. This is a parabola. So this is y square is equal to 4ax. So now let's just look here. This is x-axis. And now if we hold the this parabola through this x-axis, it will cover to each other. So now this parabola is symmetric about x-axis. The second about y-axis. If all the powers of x are even in the given equation of the curve, then the curve is symmetric about y-axis. For example, x square is equal to 4ay. Just look here. Here, this is the y-axis, and about this y-axis, this curve is symmetric about this axis, because if we fold with this y-axis, the curve will overlap to each other. So this y-axis is the curve is symmetric about this y-axis. About both x and y-axis. So if all the powers of x and y are even in the given equation of curve, then the curve is symmetric about both the axes. For example, x square plus y square is equal to a square. It is a circle. So just like here, it is symmetric about x-axis as well as it is symmetric about y-axis. About opposite quadrant. After replacing x by minus x and y by minus y, if the equation of the curve does not change, then the curve is symmetric about opposite quadrant. Let us take one example, xy equal to c square. So if we replace x by minus x, y by minus y, then it will come minus x into minus y is again xy, which is equal to c square. So this is called rectangular hyperbola. So just look here, this is the shape of the rectangular hyperbola. Clearly, what is the shape in the first quadrant? We have the same shape in the third quadrant. So this is called symmetric about opposite quadrant. The third point are fifth symmetry, which is about line y equal to x. After replacing x by y and y by x, if the equation of the curve does not change, then the curve is symmetric about the line y is equal to x, or it can be also say that it is opposite quadrant. For example, x cube plus y cube equal to 3xy. Just look here. Here, if we draw this line, just look here, this is the line y equal to, this is the line y equal to x. So this line y equal to x divides the whole curve exactly two parts. So this line y equal to x is the symmetry about line y equal to x. So this curve is symmetric about the line y equal to x. Similarly, about line y equal to minus x. After replacing x by minus y and y by minus x, if the equation of the curve does not change, then the curve is symmetric about the line y is equal to minus x. Now here xy is equal to c square. This is the one curve. Now if we take this example xy equal to c square, so here this is again a rectangular hyperbola. Just look here, this is the line y is equal to minus x, y equal to minus x. So this rectangular hyperbola is symmetric about this line y equal to minus x. So this is about the symmetry. So we have to check all six symmetries to trace any curve. This is the first point. The second point is origin. If the origin 0, 0 satisfies the equation of the curve, then the curve passes through the origin, or if there is no any absolute constant terms present in the equation of curve, then the curve passes through origin. Just look here. This is the parabola. So now here, if we write down the equation of parabola, x square, which is equal to 4ay, 4ay. So now in this parabola, there is no any absolute constant. This is x square. Absolute constant means only the term which is constant term. 4a into y, this is again a variable term. So if the absolute constant or constant terms absent in the given curve, we say that the curve passes through origin. Now, if curve passes through origin, then is it possible to find out the tangent at origin? So yes, if the curve passes through origin, then the tangent at origin can be obtained by equating the lowest degree term is equal to 0, which is called Newton's method. Let us take one example. Here, y 2ay square minus xy square equal to x cube. So what is the lowest degree term? It is 2ay square is the lowest degree term. So if you take this 2ay square equal to 0, we have y square equal to 0 or y equal to 0. So this purple line y equal to 0, this is not, this is y equal to 0 or x-axis. So this is the tangent of this given curve at origin. Is origin at this point, at origin, the line x-axis are the line y equal to 0, which has the both they have the same meaning. Either we can say that it is x-axis or line y equal to 0 is the tangent at origin. The next thing is intersection with the coordinate axis. So if we put x equal to 0, we get the intersection with y-axis because in y-axis x is 0. And if you put y equal to 0, then we get the intersection with x-axis. We also try to find the tangent at these points. Now just look here. This is the y-axis, this is the x-axis. So if we put x equal to 0 over here, we get the intersection with y-axis. If we put y equal to 0 over here, we get the intersection with x-axis. Nature of the origin. If the origin is double point, then if two separate tangents exist, then the origin will be node. But if we get single tangent for two branches of the curve, then the origin will be cusp. Now just take, this is here, we have already taken this one. There are two different tangent at origin, so it is node. Similarly, here we have only one common tangent at origin, so this origin is cusp over here. So this is about the second point, origin. The third point is asymptotes. So first thing, what is the meaning of asymptotes? Asymptotes are the straight line which is finite distance from the curve but touch at infinity. There are three types of asymptotes. The first one is called parallel to x-axis. Asymptotes parallel to x-axis can be obtained by equating the coefficient of highest degree term of x is equal to 0. Now, here, this this line x-axis is a asymptotes for the given curve. Why it is asymptotes for the given curve? Why? Because it is finite distance. Let us see, suppose the distance of this is a. It is finite distance from the given curve, but it will touches at infinity. So such type of straight line here x-axis is called the asymptotes. Now, since it is parallel to x, or we can say that it is x-axis itself, so this can be obtained by equating the coefficient of highest degree term of x equal to 0. Parallel to y-axis. Asymptotes parallel to y-axis can be obtained by equating the coefficient of highest degree term of y is equal to 0. Now here, just look here. This is the equation of 10 tangent curve. So this is the one line or asymptotes which is parallel to y-axis, and it is very finite distance from the given curve, but it touches at infinity. Similarly, this is also the uh, asymptotes for the given curve. Now, another is the oblique asymptotes. Third asymptotes is oblique asymptotes. Asymptotes not parallel to both the axes are called oblique asymptotes. Like that, this is what? This is this red line. This red line is again asymptotes of this curve because it does not it is not parallel to either x-axis or y-axis. So such type of asymptotes are called oblique asymptotes. The next thing is the spatial points. If the curve is symmetric about the line y equal to x or the line y equal to minus x, then we can get the spatial points. If we have spatial points, then we try to find the tangents at that points also. Now just look here. Here, this curve is symmetric about line y equal to x. So we are able to get one point, which will be the some spatial point. Some spatial points which can be obtained from the given equation of curve. Sometime we can directly find out the spatial point solving the given curve equation of the curve. For example, here these 2 points are spatial points over here. The last point is reason of absence of the given curve. If possible, we try to express the curve in explicit form. If for any value of x, y is imaginary, then there is no part of the curve for that value of x. Similarly, if for any value of y, x is imaginary, then there is no part of the curve for that value of y. Let me take one example. Suppose we have given y square equal to x square, a x square times of a minus x whole divided by x plus a. So here we can write down y equal to x root a minus x upon root a plus x. And if we want to trace this curve, we are getting, just look here, this is x is equal to, this is x is equal to minus a, and this is x is equal to plus a. So clearly, if we see that the curve is not beyond the line x equal to minus a to x equal to plus a. So this is what this region and this region, they are the region where curve will never exist. So this is about the region of absent of the given curve. So now if we follow all these four properties or 4 points, then we are easily able to trace the any Cartesian curve. Thank you.